Okay, in this section we're going to use the knowledge of the work that we've done in calculus and differentiation and apply that to problems including motion. So if you look at this graph of y against x, we can see that it has a maximum, and if we find the gradient function and set that equal to 0, then we can find the value of x where that maximum occurs. We're going to use this in the setting for displacement. So if you look at the same graph, but this time it's displacements against time, you'll see here that the maximum refers to the gradient function ds by dt, which represents velocity, and that's when the velocity is equal to 0. This is the maximum displacement. Other things that are going to be useful, or we recognize that t equals 0 represents our start, and at this point in time here the particle has returned to the starting position. The displacement is now 0. So in this region here, displacement is positive. This question involves a particle leaving the origin and moving along the x-axis, and at time t the velocity is given by this equation here. We have a restriction for time between 0 and 6. Looking at the graph, we can see this is a square, this is a square, so it's going to give us a quartic function. Part A, sketch a velocity time graph for the motion of p. Let's just recap our knowledge on quartic functions. It's a positive quartic function, and it's going to give us this classic W shape here. We may have some double roots here and double roots here if it doesn't cross the x-axis. Let's find the solutions for that. So we've got t equals 0 as double root and t equals 6 as a double root, and this is our graph. Now you see I've crossed out when time is greater than 6 and when time is less than 0. So that's not a valid part to our model. Our model only refers to the velocity between this interval here. The next part, we've been asked to find the maximum value of v. So the word dv by dt is equal to 0. It's going to refer to this point here, so maximum, we can see that, and that's in the range as given. So what I'm going to do here is just expand out the equation for velocity so it's ready or prepare it for differentiation. So dv by dt gives me this. I want to set this equal to 0 and factorize. So I have one solution here, t equals 0. I'll factorize this to give t equals 0, t equals 6, and t equals 3. Now looking back to the graph, I know that this refers to the maximum, so the time t equals 3. Let's substitute that back into the original velocity equation, and we get a maximum value of 81 meters per second. We're now ready for you to do the exercises associated with this. In this section we're going to use what we've learnt about integration and find the area under a curve. So previously we would have sketched a graph of y against x, and if we want to find the area between the limits 0 and 5, we will integrate y with respect to x between those limits to give us the area. And we can use the same principle with the velocity time graph, as we know that the velocity time graph gives us displacement, or positive displacement is the distance. So we're here to find this area. We're going to integrate the velocity with respect to time between the two limits of time from 0 to t. Let's take a look at the question. So this particle travels in a straight line, and after t seconds its velocity is given by this equation here. Now what we need to do is to be really careful that we don't cross the x-axis, otherwise we'll have a positive displacement and a negative displacement. And be careful when we were integrating, we'd recognize that we would be adding the two values together after removing the negative to give the total area. In this particular case, we've been asked to find the distance. So let's sketch the graph first. So the usual practices. I've found that the solutions are minus 1.9 plus 1.29, and we have a maximum here of equals 5. It's a negative quadratic. Now the distance travelled by the particle in the third second of its motion, so this is the first second, this is the second second, this is the third section. So I know I'm going to be integrating between the limits 2 and 3. So I'm looking for this. And although it's going to be a negative displacement, We just want the distance, so we'll just convert that into a positive value. So we set up the integration with the limits 2 to 3, put it into the square bracket form, power of 3, 2, simplify, and then evaluate. And remember, any integration that I'm going to be evaluating, I'll do it on my calculator as well. That gives us negative 15/4, so therefore the distance is 3.75 meters. You can now have a go at the questions. Okay, well done, you've made it to the end of the video. So this is our final part, constant acceleration formulae. And what we're trying to do here is to use calculus to actually derive the Suvat equations. V equals u plus at and s equals ut plus half at squared. So we're going to use some initial conditions. And if we look at our standard graph for velocity and time, we can see at time t equals 0, the velocity is u. And at time t equals 0, our displacement is 0. So we have constant acceleration. So if we integrate acceleration with respect to time, we should get velocity. That gives us v equals at plus c. But our initial conditions, as we stated, when t equals 0, v equals u. Substitute in, we then get v equals u plus at. Let's look at our second situation. If we want to find displacement, then we're going to integrate velocity with respect to time. Once we've done the integration, we use our initial conditions, s equals 0, t equals 0, so therefore c is equal to 0. So we have a final equation for displacement, which, as you can see, is one of our Suvats. And that's as much as we need to be able to do for this section to be able to complete the remainder of the questions. Okay, good luck.